Great. Hi everybody, I'm Dave Stark. I'm a postdoc at Hadley IPNU. Thank you to the organizers for letting me speak to you today. So I'll be talking to you about multi-scale environmental influences on galaxy gas and content. So really changing scales here, going really into the large-scale environment around galaxies. Just want to quickly acknowledge my collaborators on the work. So just to set the stage, we've talked a lot about environmental processes and how these can affect galaxies, particularly their fuel supply. So there's processes that can replenish gas supply, like cosmological accretion, gas-rich murders. Then the other side of this is that there are a number of processes that can remove gas or cut off the inflow and cause the galaxy to exhaust its gas starvation. So one question that's still out there is that so these processes, these depletion processes, have mainly been studied in high mass groups and large galaxy clusters. So there's still the question of how important are they in the low halo mass regime. And in the last 5 to 10 years, there's been a growth of studies that have really looked at the environment going beyond the scale of individual halos and going and looking at the large scale structure. So how do interactions between halos actually affect their fuel supply? So you can have flyby interactions, there can be competition for gas accretion, where there's a strong tidal field. So in simulations showing ram pressure stripping of halo gas, there may be variations in IgM temperature, and then this general idea that there's halo assembly bias, so halos in overdense region form earlier than those in underdense regions, and that could be reflected in the properties of galaxies like their gas content. So the key questions I'm trying to address are group scale processes that lower gas content, are those effective in low mass groups, low mass dark matter halos? And is the gas content entirely regulated by the dark matter halo and the internal environment? Or does the larger scale environment play a role? So to address this, I'm using the Resolve survey, which is a program I've been a part of for the last several years. This is PA'd by my former PhD advisor, Sheila Conklin at UNC. This is a volume-limited census of galaxies in the local universe. The idea is to get a mass census, a velocity census, star formation analysis, so everything you want to know about these galaxies to account for all that. And it's designed to be a statistically representative subset of the local galaxy population. So we've improved the completeness over SDSS, particularly at the low mass end, so we're pushing down to a completeness limit in baryonic mass of about just above 10 to the 9th, and stellar mass just below 10 to the 9th, so we have about 1,500 galaxies to work with. What I have been leading is the atomic gas census, which is just a part of the Resolve survey in general. And so the goal here is, that, like the gas survey that Barbara was talking about earlier, we want to get a good constraint on every single galaxy's gas content. So this is not a flux-limited survey, but if we don't detect a galaxy, we push down to a very good upper limit. Our upper limits are not as good as gas, but we do constrain the gas fraction to less than 5% typically, or up to 10% of the stellar mass. And it's going pretty well. We're very getting toward 95% complete now. There's going to be a big H1 catalog release soon, so I'll just advertise that. Now we can combine the gas census with a number of environment metrics that parameterize the small to large scale environments. So just to quickly summarize, we identified groups using the friends of friends algorithm. We then assigned masses to those groups using the halo abundance matching technique, where we use the integrated stellar mass of the entire group as the proxy for the halo mass. We then use those groups, their masses, and the positions, and estimate a relative large scale structure density around each group. And lastly, we run the second rounds of the friends of friends algorithm on the group catalog itself, and we pull out large scale structures. And then these are visually classified, but they do show some interesting differences, which I'll show you in a bit. But this is the two Resolve footprints, and then these are the different types of structures. So the large scale filaments are shown in green, walls are shown in orange. There's this big category of blob, which means I don't know what to call this thing. I don't know what it looks like. I won't really be talking about those. We have clusters in purple. We define them as halos greater than 10 to the 13th. I realize that's kind of low. We don't have that many of them. And then unclassified objects. So you can see there's a lot of diversity in the environments and the densities. So first, going back to the halo scale, the first thing to look at is, so what's the influence of the dark matter halo on the gas content of galaxies? So what's plotted here is the gas to stellar mass ratio versus stellar mass, broken up into different halo mass regimes, and also broken up into centrals and satellite galaxies in the solid and ash lines. And so what you can see, and this is consistent with what we've seen earlier, is that at fixed stellar mass, as the gas content, or as the halo mass increases, the gas content in the satellites goes down. So we think we're seeing this effect down to a halo mass scale of about 10 to the 12th, so this is Milky Way scales. And on the other hand, if you look at the central galaxies, you'll see that there's a very smooth relationship between gas to stellar mass ratio and stellar mass, with no secondary halo mass dependence, but I just want to stress that this is really built in. Just to illustrate this, because we're using halo abundance matching, where we're using the integrated stellar mass to get at the halo mass, the central galaxy is going to dominate that stellar mass budget. So basically, we're building in a close tie between stellar mass and halo mass. Now, if we come at this a different way and we do halo abundance matching with baryonic mass, we get a different relationship. We don't know which one of these is right. We're sort of taking an agnostic approach and saying, basically, we can't disentangle the behavior of centrals from the way we're estimating halo mass. But for satellites, things are a little better because we do see some consistent behavior in that we see the gas fraction declining, at least down to, systematically declining, at least down to 10 to the 12th. So now moving beyond the massive halos, looking at the larger scale environment, what I'm showing here is the median gas to stellar mass ratio versus halo mass for centrals and satellites, broken up into large-scale filaments and large-scale walls. And this is just a visual classification of filaments and walls, but they do show some interesting differences. If you just look at the solid lines for now, you see that filaments are more gas-rich or walls more gas-poor at fixed halo mass in these two different large-scale environments. Now we look to see whether this is dependent on how we define the halo mass, and this seems pretty robust to our halo abundance matching approach. We also explored whether or not these at fixed halo masses just different stellar mass distributions in each of these halo mass bands. So filaments and walls have different stellar mass distributions. So what we did is we predicted the relationship if you just predict the gas fraction from the stellar mass distribution, and that's what's shown in these dashed regions. But they don't show the same offset that we see in the data. Now, not all walls and filaments and aspects of large-scale structure are going to be the same. There's going to be low-density regions, high-density regions. So what if we just look at the gas fraction as a function of large-scale density? So what's plotted here is now it's switched up a little. It's the fraction of gas-poor galaxies with gas fractions less than 0.1 versus the large-scale structure density, and this is a relative density. That's why the middle is 0. And this is broken up by halo mass, and also broken up, it's basically broken up into 3 density regimes. So you have underdense, medium density or average density, and then overdense regimes. So below the halo mass scale of 10 to the 12th, we do see a clear dependence of the fraction of gas deficient galaxies as a function of large scale structure density, independent of their halo mass. Now interestingly, if we look at the filaments, this correlation disappears. So for some reason, the filaments don't show the same dependence on density, the large scale structure density, but the walls show a very, very strong dependence on the large scale structure density. So this is really interesting. It's hard to explain right now, but this is what we're seeing. Another thing I'll point out is that if you look at average densities, if you look at the, if you fix mass, halo mass regime and you fix the density regime, we actually still get differences between filaments and walls. So it's not that we're sampling different density regimes of filaments and walls. We fix both those quantities. We do see these different levels of gas deficiency. And another thing we see is that a general thing we see is that in these blue points, which are very low halo mass galaxies, down to 10 to the 11th or so, these are galaxies that we typically expect to be actually gas dominated, so have more gas in, more mass in gas than in stars. But we're seeing this non-negligible fraction without any that are gas deficient. So what's causing this? And we get a clue from looking at the positions relative to other galaxies, or to other groups. So what we find, what this plot is showing is the relative distance between our gas-rich and gas-poor, low halo mass central galaxies, showing the relative distance to the nearest significantly larger group neighbor, which is a group greater than 10 to the 12th. You can see that the gas-poor ones really cluster close to the nearest more massive group. And we've already corrected this for effects like fragmentation or overworking the friends of friends algorithm, so we think this is a robust result. And what this might indicate is that the low mass halos are having flyby interactions with the larger halos that is then cutting off their gas supply, so they may be starving that way, or there's some sort of competitive gas accretion where when you have a low mass halo in close proximity to a much higher mass halo, Basically, that high mass halo takes all the IgM gas and the low mass halo can't get at it. So I'll also point out these are mostly found in the large scale walls, so that might explain why we see, be part of the reason why we see them being on average more gas poor. And another thing we can just a really open general question is, well, should we be changing our definition of where groups end? So recently, Serco More has proposed a physical definition of a group's edge, which is the splashback radius, which is distinct from the sort of typical R200 that people use, 200 times the mean matter density. And what we find is that our gas poor centrals, so we think they're in their own halos, but they're falling inside this splashback radius of the nearest larger halo. So we could be, maybe we should just be considering these satellites, and we should be updating our definition of a group to account for this event. So I'm going to skip this last slide. There's a lot of speculation, and I will leave you with my conclusions. Thanks.
Hi, very nice. Okay. In the maps you showed the names of the large scale structure, it's quite easy subjectively to identify the filaments and where this stuff in groups are. But it's much more difficult to do this objectively, quantitatively. So can you tell us how you define filaments, especially when you get near the clusters?
So let me go back to groups. Well, if I can find the maps. So I don't know what button I did. So how we identify the filament? So once we get out to these, I just want to show that slide. Not it. Yeah, thank you. So how we identify the filaments? We don't actually do it in projection. We look at the structures in 3 dimensions. So we have the redshift information. Again, assuming there's some redshift distortions, but we're also just looking at the groups, and so that minimizes some of the redshift distortions. Now, when we get to the clusters, what we actually do is we mask out the clusters. So hopefully what we're seeing is just the parts of the filament that are coming off of that. And so, does that answer your question?
More or less, we can discuss.
Okay.
So many of your trends seem to reproduce pretty much what we have seen in terms of the variations of the environment. And since we know that the H1 goes with the star formation, this is pretty much what we expect. To really disentangle the different environmental effects, the key is to look at fixed stellar mass and fixed star formation, because then you get an handle of the time scales. Did you ever look at this, and can you comment on what you find?
We tried, but like Robert talked earlier about statistics and having enough galaxies, and that's the issue for us as well. But yeah, I don't agree.
Just quickly, I was wondering if you've compared any of your results for how gas fraction varies as a function of environment with either semi-elliptic models or hydrodynamic simulations.
No, but I need to because I've been suggested that like 10 times now. Yeah, it's definitely something I want to do.
Lots of people through, you're probably up with that.
Yeah, so that's a great idea. Yeah.
I'm very clear afterwards.
Other question? Thanks again.